Good morning, everyone. I hope you are well and in good shape to continue this session. My name is Evan, and I will be the moderator today. Before we start the lecture, I will introduce our invited speaker, Dr. Hakim Lutfi Malasan. He is a faculty member and senior lecturer at Astronomy Study Program ITB, and also the director of ITERA Lampung Astronomical Observatory. He earned his degree in Bachelor of Astronomy from ITB in 1985, and then he went to the University of Tokyo and earned Master and PhD in Astronomy in 8 years. Since then, he has been actively researching in several fields of studies, such as stellar physics, photometry of variable and eclipsing binary stars, spectroscopic studies of emission line objects, development of CCD-based astronomical instruments, and image and data processing in astronomy. So now we welcome and we invite Dr. Hakim to deliver his lecture in time series. If you have question, you can raise your hand and I will notify him. Pak Hakim, please.
Yeah, thank you very much, Evan. A very good morning to everybody. I hope you are all healthy. This is the end of the week. So there will be two situations that you are going to encounter. Either you are boring because of the previous lecture, or you are quite in a high spirit to welcome a new week with so many new knowledge you are going to acquire. So as you may see that I'm quite not appear too young to you. So I'd like to have a bit relaxed session at the end of this week, and the topic bestowed upon me is time series, which is of course not a very easy topic to deliver, but let me share you as an ice breaking my personal recollection. I think you haven't found it in the folder yet. I uploaded that just last night, and I think it would be good to share this experience to you on when at the first time I did encounter the problem of time series, and I had a hard time on that time. It was 30 years ago. So what I like to share to you is a personal recollection of an astronomer or a new astronomer like you. I was at your age, on how I faced the problem and how actually I tried to gain my knowledge on these new problems and solve the problem and publish the paper on that. So let me share a slide. This is supposed to be a relaxed session before we go through the time series methods and all related things. So Evan, if you permit me to show my slide to all the audience.
You can.
Yeah. Okay, so let's start with the warming up session or ice breaking. I prefer ice breaking session, and you of course may open your mic and ask if you are curious to know more about this, because this is not supposed to be a very time series topic. We are going to enter this topic later after I have this ice breaking session. The purpose of this is try to share my experience to you. The title here is a personal recollection on my hard time series analysis that I happened to face 30 years ago when I was at your age, with a very different situation. Okay, so what I wrote here is a work that I carried out 30 years ago to reveal triple star nature of the central star of a planetary nebula. So when you look at the system itself, what comes to your mind is there are so many periods actually pertaining in this system, because they are triple star and every star orbiting each other. So, and one star may have its own property, okay, and this two star moving around the triple star, that of course introduced us to another period. So I had this problem when I was at your age at that time. So I was a master student. You may see my face here with a very different appearance of the hair. It's not a silvery hair. I didn't paint my hair, don't believe me. So I was a master student in 1980, 87, 30 years ago at the University of Tokyo. And my passion was and is stellar physics up to now, and especially observational, observational study of closed binary systems. As you may see here, that is my room, my desk with so many books on the shelf, and there is a computer there. That's not my own computer. I have no privilege to have a computer on my room, so I have to go to the computer center. I have to, of course, enroll, wait for a queue so that the supervisor may admit me to go and have a privilege to push the button of the workstation operating Unix operating system there. That's the computer center at the National Astronomical Observatory in Japan. So my supervisor is a very dynamic man, very energetic man. So he challenged me with the topic of binary central stars of planetary nebulae. I did binary work actually since I was an undergrad student at Bosca Observatory. Mostly I did a photometric observation using photoelectric photometer on that time. Then I made acquaintance, of course, with the spectroscopy in Japan using the 2-meter telescope at Okayama Astrophysical Observatory and Dodaira Station at at somewhere in Saitama Prefecture. And my supervisor in 1985, he went to Mauna Kea and used the telescope, 60-centimeter telescope, to carry out the photometric observation using photoelectric photometer. So that's a challenge that he offered me. And if you look at how the paper published, it went through a very long process. The central star of planetary nebula, the Longmore Triton 5, is a central star of a low surface brightness planetary nebula with a high galactic altitude. That is the simplest way to do photometry. So we have a very strong selection effect because of the limitation in the technology on that time to observe a central star of planetary nebula. But we are very much interested on the variability of the central star of planetary nebula. The central star name IN, in the International Bulletin of Variable Star nomenclature, but it has also the SAO nomenclature, SAO number, and Henry Draper. So the central star, it's very strange because based on observation, how come that the central star of planetary nebula has a spectral type of G5, giant? So there is hypothesis that it should be a binary or even a triple system. So if we go to the binary, it's quite useful because several binary system has been found. But what about triple system? So this is actually the hypothesis. So the work started in 1985 when my supervisor collected all the data through photometric observation. And I came to Japan in 1987 and engaged in this work since then. Then I continued the photometric observation and spectroscopic observation, mostly optical. And basically that's a time series observation. We monitor the spectra and the light from the system. Then in 1989, I start writing the thesis and make a time series analysis, which is very painstaking, make an interpretation and proposing triple system, which is even more painstaking for me. Then I graduated as a master's student, graduate from master's student in 1989, and the draft of the paper, and as you know, University of Tokyo has a very high standard. They ask the student to publish the paper. And then, well, it took 1 year to publish this. So the paper was submitted, draft of the paper submitted in February 1990 and got published in 1991. Very long revision, back and forth from the referee. So the question is why it took a long time for that. So let me see here. Oops. Yeah. So it took 1 year. As you may see here, the paper draft was received in 1990 February and revised in February 1991, and finally got published as in Astronomical Journal, volume 101 that time. So, of course, there is a question why it takes such a long time. Let me show this. Okay, can you still see my slide?
Yes,
Yeah,
it's good.
good. So the question is why? When we come to propose the system, and it turns out there is a nebula here, and there is a central star, true central star that we propose to be in the third as the third body of the star. The central star of planetary nebula is very faint, an SDO type with a very high temperature but very low luminosity because of the small size. It's a white dwarf. It's going to be a white dwarf. So that's the true central star that we hypothesize. And what can we observe is, of course, the bright G5 star here. And in the binary zoo, actually G5 star as a component of binary system may belong to the RS Canven closed binary star with a very active chromosphere here. So the question why is because first, multiplicity in the central star of planetary nebula has been pointed out by some astronomers before. And so that's why we need a follow-up, or we have to monitor this by means of photometry and high resolution spectroscopy. But when I look at the previous publications, so many periods has been published. Before I start working on this, I found 4 periods proposed by astronomer and very confusing. So we may think because of the system itself is complex. So that's why we are very much interested to disentangle the nature of multiplicity as a central star of planetary nebula. And remember, on that time, the concept of stellar evolution is mostly heavily on the single star evolution, not in the binary and multiple system, unlike now. Okay. So that is the reason why we are so interested in studying this. But when we go through this, we found that time series analysis is very difficult because we have to, of course, decompose or try to identify the exact period of this system, of this whole system, and of course, for this particular star with the spot here. So there are 3 causes of this: difficulty in determining period of the closed binary system itself, difficulty in determining period around the third body, and complication in the light curve due to chromospheric activity. That is the whole. But what about my situation on that time, back in 1988? I know nothing about time series analysis except the O-C analysis, which is a very primitive way in doing time series analysis. It was not really written, of course, in the book now, but it used to be an overwhelming method, mostly by stellar physicists on that time. That's the only, I may say that's the only tool for closed binary worker to carry out the time series analysis efficiently, mostly by observer on that time. And second, no privilege in having personal computer at my disposal on that time. Computer was so expensive on that time, so I was only able to use the mainframe or workstation at computer center. And I know nothing than basic and Fortran on that time. And of course, no R, right? Then no Fagelson and Babu's book, of course. Mostly all time series recipes, algorithm are embedded in the journal, in the publication. So I have to scan this. So the result of my scanning and my literature study are also put up in the folder. You may retrieve it if you like. That is based on my extensive survey up to the year 2000. But since then, I found that mostly of the publication based upon this 4 or 5 aspects that I try to group all the literatures, because there are so many publications about time series analysis. So what we try to do after we learn this is first, we try to look at the data. Look at the data is very important. That's the first thing that you have to do when you deal with time series analysis. Despite of course, even if you have so many methods that you know, the first thing to do is look into the data. Our data was so complicated on that time. We make 5 years of observations, 3 years, including previous publications, and when we try to plot this in one curve, we found this is very confusing, like no pattern whatsoever. And then what we try to do is, try to, of course, experiment in all the data. Although we are using the most popular tools on that time, the Scargill method based on discrete Fourier transform. And there is also improvement of Scargill method by Horn and Baliunas in 1986. They tried to normalize Scargill parallelogram into the total variance of data in order to make to give the better result of the peak and the power spectrum. And it's not really easy just put this into the program and run it and get the power spectra. At first, I didn't get this power spectra at all. I found a so confusing power spectra with no peak. Then we try to separate in each filter, analyze the parallelogram for U filter, B filter, and V filter. And moreover, we try to separate observing run from the previous observation and our observation. And then what we did is to multiply this. So multiplying parallelogram caused an upset of the referee. He didn't accept this. So we have to fight with him. Try to, of course, retain our reason. And that is one cause why it took a long time to publish this, because there are many disagreements on using this method. Time series was not as mature as now at that time. And then, even that, if you look at this, the common sense when you look at the parallelogram, you may always think that the highest peak would indicate the best period, but it is not the case in our observation, in our work. We found that the true period is not this one, but this one, the one with the red one, which is not a very high peak. It's lower than this one. And the others are aliases of this frequency that we identified here. And then we try to convince because it's in line, of course, with the previous publication. And luckily, we have a confirmation of observation from the other observer. So that's why our claim that this period of 1.2001 days is correct. But then the interpretation is, what is this period? That comes later. So this is more or less the way that we try to find the best solution to overcome the very strong heterogeneity in the data in order to get the most representative power spectra, and moreover help us to detect or to conclude what is the best period that can be deduced from this analysis. Since this is a chromospheric active stars, so there are many disturbances in the light curve. The phase shift is caused by shift of the spot of the star, because the ephemeris of the light curve different from time to time. So that's why we have to introduce one other recipe, is to make a phase shift in the phase curve in order to match all the light curve into one ephemeris and get the final light curve like this. This is a very convincing argument that we can give to the referee, that of course the referee on that time accepted this, and finally we get published. So yeah, of course, the story is not rely only on photometric observation, but we also have this spectroscopic observation. Well, spectroscopic data is also difficult for this star. As you know, this is a G5 giant star. Cross correlation method, for example, as a method, which is a very common method now, on that time was still difficult to implement it because of lack of computer power on that time, of course. And most of astronomers are rely on the old bisection method. But then when we face with this spectra, of course, cross correlation is mandatory to do this in order to get a better radial velocity. Then I collect all the radial velocity, measure this from metallic line and the H alpha line. The H alpha line appearance is also very strange because it shows us not absorption line like this, but instead emission line with double peaks. So that is why the spectroscopic itself is a very painstaking process in reducing the data and come to the tabulation of this radial velocity that we feel the best from our measurement. So this go into this Horn and Baliunas and Scargill method again. and we analyze, but this is easier compared to the light curve one, because then we conclude that period is 1.7545 without any objection from the referee. But the referee didn't like to see the the radial velocity. But this is mostly due to the low signal to noise ratio. So that's why we have many scatter. But despite of scatter here, we found that this is the radial velocity of the inner system of LT5. So these two time series was the most painstaking process that we did for this nature of data. And what we did actually, we tried to split this data into 6 annual data sets and perform periodogram analysis for each of the data set. Of course, you may feel a bit worried to see in 1987, for example, we have only say two data. Of course, we didn't use this, but mostly we do this for all the data. And we try to match one of the data. The reason is very easy, because it is a triple system. So one of this group of data may show you very different systemic velocity because of the movement of the double system, the binary system on the third body itself. So what we did is try to construct the periodogram, conclude or try to get the idea of the period, and then plot the radial velocity curve. Yes. And there are two, of course, theoretical radial velocity curve that can be assigned here. First is if we don't introduce any weight in the data, and the second if we use the weight, the lower weight for the open circle and larger weight is for the dark circle, and then we get a better radial velocity here. This is not an eclipsing, so that's why you may not see any eclipsing in the light curve, and of course it may be inclined. It's not really inclined, so that's why the amplitude of the light curve is not really big here. But then from the systemic velocity, we can also construct. This one goes without any time series analysis, but it's just an eye fitting, and then we conclude that there is another period for the triple system, which is 2000 days. So that is the long journey that we went through for almost 1 year. When well, preparing itself may take about 1 or 2 months, but try to convince the review to get published takes another length of time. So what is the lesson learned from here? Time series analysis is indispensable astronomical observation. It's very indispensable and time consuming too, because using the tool to analyze the data is easy, but how to interpret this? You need a very good insight of astrophysics along with time series analysis. So you cannot just think that time series is a machine in which you put all the data there and then inspect the result. You may of course feel frustration when you look at the result, which is not in line with your astrophysical hypothesis. And you need a lot of experiments creating observational data. Sometimes you have to think out of the box and try to find a new way in handling the data before you input this into the time series tool. And remember, you have to be very careful with the very basic of time series, which is the window effect, the length of observation, which can be too short or too long for any variability that it could cover, the noise that always with the data together, resolution, aliases, and many non-sinusoidal patterns. You cannot simply assume that all variation is sinusoidal. I may say that 60% of astronomical phenomena is mostly non-sinusoidal, but even though Fourier transform is still powerful. And most of all, convince the referee that you are doing analysis in a correct way and the result is strong. So many opportunity can be obtained since for the referee and for us, astronomical study always presenting something new for us. So that's a good spirit in astronomy. And I like to close this by showing you when I was young, I was a football player in Tokyo. This is my group. And we always imagine that playing football is like writing a paper. You have to go through many players. You have to, of course, sometimes make some improvisation to carry the ball from here to here and finally get to the goal and make a goal. So that's what I like to share to you. And of course, if you like to chat with me on this matter, I give you time. Before I go to the real lecture about time series analysis. So if you have question, please.
Okay, if participant wants to ask something, please raise your hands. Okay, Arifin, you may ask.
Hello, am I audible?
Hello, Arifin.
Yep.
Yeah. Okay.
Morning.
Thank you for the great story. Actually, I really like this personal journey. So I'm curious, Dr. Hakim.
Yes.
Are those 30 years or maybe those bitter experience made you more in love with planetary nebula, or that made you like, okay, I'm gonna stop doing planetary nebula and the time series analysis? Does this hardship makes you more in love, or when she wants to run?
That's a very good question, Arifin. Yes, I'm still in love with it in the nebula, because when you start with the hard problem at the beginning, that actually gives you a fighting spirit of course, in tackling many problems after that. So it's a very good. Well, imagine that you are a soldier, then if you have a lot of ammunition at the beginning, yes, and you try not to shoot anybody abruptly. you can shoot any enemy abruptly, but you can aim at the very precise target on that time. So it's painstaking, because in order, well, think about the sniper, how he must be very patient, endure, yes, and then he try to hit the target precisely. I may not be so perfect on that time because I was so young, but you are true. After I finish all this and get published after 1 year, I used to think that I like to change subject to the other, which is more easier, more instant to publish at that time, because it's also something that I have to do with a very short duration of PhD course on that time. But no, I decided to continue, and I did my PhD work also in the multiple system of planetary nebula at that time. But the problem is we need a large telescope for that. But now, lucky that we have so many telescopes dedicated to observe planetary nebula, and I'm still in this business actually until now. But I found that time series is much easier to implement now. But the message that I like to convey, no matter how easy time series can be carried out now, you have to be very careful with the data. Yeah. Not think about pour all the data into this time series machinery and get the result, because then you may hit the stone there, hit the wall there, because you may see the very funny periodogram. That's the hardest thing for you. And then you have to go back and look into the data again and try to say not manipulate the data, but actually try to do something with the data. And when you try to do something of the data, don't be afraid that you are thinking out of the box or you are violating the fundamental statistical sense. Even in astronomy, all the time series can be devised to handle small number of data, say 5 data only, which is maybe for people in the other fields, they feel quite strange, because when they do, say, the economists always do time series for thousands of data, but in astronomy, only with 5 and 6 data, we have a very strong tool to do that. So that's why I'm still loving time series, but it is because I'm getting older, so I'm not as fast as you in grasping into many new information. Time series flow of information is very high. The last paper that I saw is a very good paper, or not, exposition about the people who are using Kepler for time series analysis in astronomy. That's very good. I would recommend you to read that, how they use this for asteroseismology study. But then when I look at the basic, they are still based on the methods that I'm going to explain to you later. So that's my story, Arifin, about this. And I hope this can be valuable for you, because you are young. You may go through this process. You may find a hard problem. So my suggestion not to escape from that problem, try to solve that problem. The challenging problem is very interesting for your life.
Thank you very much, Dr. Hakim.
Yeah, thank you, Arifin. Yeah.
Okay, any other question? Okay, I think we can continue the lecture, Dr. Hakim.
Yes, thank you very much, Pak Evan. I have to find where is my slide. Give me time, please. Yes. Now we go to the time series analysis in observational astronomy. Yeah. Okay, so I will start this from here. Yeah. So the lecture start, and I have a half day in the morning session together with you on this topic, time series analysis. I try to finish this within maybe 2 hours. So we're going to have the break in the middle, Pak Evan. And then at the second session, after finishing all the contents here, and I think some of you may already have these slides with you, then we come to the hands-on. I'd like to introduce you one simple problem in time series, which should be easy for you to try to exercise yourself to analyze this problem. And at the afternoon session, you're going to have one session in which you can work on your own. A tutor will be with you, and then try to solve this problem in the hands-on that I'd like to deliver to you. So from now, yeah, let me mostly occupy this class by my talk, but then of course I will invite any question if you like to answer to ask to me. So first of all, let's look at the one fundamental thing, the impression of us to the sky, and what makes people think time series is so important. That actually time series exists from a long time ago, but we just make this as a new knowledge very recently for us. So think about the sky. The sky remains unchanged for the naked eye that we observe, except for those who are very keen to observe the regular movement of bright solar system objects, rise and set of the sun. This is the observable ones. I mean that you don't have any intention to observe, but it's observable by you because you observe the sun position of the time. You feel the sun position all of the time. You may sense how the moon is in the full phase, on the crescent phase. So that things that can be felt by everybody here. But then the development of telescopes technology, especially sensitivity in the wavelength, that enable us to observe systematically by plan a number of complex variability. And what we found up to now, the range of variability in the universe start from milliseconds variation up to centuries variation. And the properties of variability is also based on two things. First is the periodicity. There are quite unique period in the system, but there is also quasi-periodic system. They're irregular that not yet can be explained, the cause and the pattern of the variability. There are some quiescent with occasional pulse like burst. Okay? And that's speaking about the when it repeats again, or the period itself. On the other side, we have also amplitude. The amplitude range from millimagnitude, the extrasolar planet transit, with a small variation until several magnitude, explosive like supernova or nova. So when we look at this, basically astronomical observation are actually not independent. They're quite depend on the variation, depend on the time and space. And variation is not independent, and variation is a function of time. From this, we may gain our sense that there is a time series analysis. There is an imperative of making monitoring or time series analysis in order to gain insight on any astronomical phenomena in the universe. Okay? So, and yes, the variability in the observed sky, when I jump into that aspect, this can be divided into two. One is the pre-modern astronomy, in which no computer, no machinery that can help in making any calculation. But even though people or mankind, well, reach a very good achievement in which they created the lunisolar calendrical system for agriculture practices, mostly in the Oriental, and Sarios period in Babylonia for solar eclipse. This was historical, but actually that give us on how mankind can achieve this when they observe the variation, the very distinct variation with their naked eye. But then we have also Mayan calendar, which is more fascinating because it's based on eclipse, how keen they observe the eclipse and the phases of the Venus. So these are all the pre-modern astronomy variability that can be detected by humankind without any help, without any instrument. But they can make a very good tabulation and prediction. So then the modern studies start from Copernican revolution, where Ptolemy's and Kepler basically they construct a non-linear. Non-linear means it's not a line, but of course something that is has a degree here. In this case, ellipse, for example. So the non-linear parametric of periodic geometry model and celestial object motions. This is actually the very fundamental of time series in the scientific aspect. So since then, we have the what's so-called the modern time series analysis, in which Tycho, on that time, we make a measurement and tabulation of planetary position. The tabulation itself actually representing a time series analysis. And the Johannes Kepler concept of relation try to relate this algebra and geometry of planets motion actually give more flavor in this time series of astronomical phenomena. So speaking about this, then what can we see the characteristic problem in time series analysis? Basically, there are two. First is the irregular and interrupted observing time. When you make observation with the ground-based telescopes, either with your naked eye, so you are very much affected by the presence of moon that actually basically they hamper you in making continuous observation. Moon phases is also very much in making precise photometric observation. Moon phases is something that we have to, of course, take into account. When you like, for example, in my experience, if you like to make a surface photometry of planetary nebula, because the planetary nebula surface brightness is very low, we need a new moon phase. But even though new moon phase, we know that planetary nebula is mostly galactic object. So there is a galactic light, of course, that may hamper us in making a very high precision of imaging of the planetary nebula. And don't forget the weather. The weather always blocks us making any observation. So that's why this all introduced to irregularity and interrupted nature in observing time when we make astronomical observation. This also happened for a space telescope, because sometimes for a geostationary space telescope, for example, they may be occulted by moon, by the Earth itself when they are in the night part and then like to observe the other side. Or if the sun shows storm phenomena, of course, the disruption may cause the shutdown, temporary shutdown of the space telescope electronic panel because of excess of charged particles. But above all, there is a very limited access to the space telescope because of the very high competition rate in proposing any allocation time for the space telescope. So this all introduced the irregularity and interrupted observing time. And remember, once we have an observing time, we observe, our data is always accompanied by noise. And this noise is different from each observation, and most of all, no universal model for observational noise. Well, the very basic one is the photon noise, but then we have our atmosphere, we have scintillation, we have seeing and everything that may cause of that. So the scientific purposes of time series in this regard is a characterization of variation in the context of physical model. So don't forget the physical model plays important role when we try to characterize any variation. You should go with this regulation, the physical models. So this also aligning you into a conclusion along with the very common physical laws that happen to all astronomical objects. So periodic orbit, pulsation, stochastic process, etc. These are all the underlying physical model upon which we have to characterize our variation. But as a result, as an outcome of time series, you are able to make a prediction. This is very important. This is the key important thing of time series, to predict that it may happen again sometimes. So, and this is very common. Think about how precise now we can predict the eclipse, solar eclipse or moon eclipse, because of the very good database of time series that we have. Even though we still have to improve the ephemeris of this from time to time. So in the course of this, many innovation of new time series methods specific for astronomical observation. I may say that the most productive way, in speaking about time series, the most productive field is astronomy, because we always deal with new data. We always deal with new yet not explained information or explanation about some phenomenon. So that's why we have to think hard about the new time series method, or try to optimize the established time series to match that. The story that I shared to you 30 years ago was really new in the world of time series. But then it's quite common after we got published this. Many people use the other recipe without mentioning, because the rate of new innovation in time series is so high. Okay, so well, have a look at glance on the data in time series analysis. These are mostly based on two samplings: equally spaced time series or unequal time series. Look at the exoplanet with 2-minute cadence of data of ES, and this is of course time when I talk about time series analysis. And Monthly sunspot number, which is not as crowded as this one because of the cadence is not as short as data in TES. The supernova light curve, which shows you sudden incline of the light curve and steady and low slope of the light curve, and all the x-axis here are times. And lucky in astronomy we have the Julian date, which is a very regular one since it's 0 point in the 16th century and still consistently used up to now. We even now have the barycentric Julian date instead of heliocentric Julian date, which is much more precise in terms of defining a period for the nature of any multiple system there. So these are some of the good equally spaced time series that should be easy to cope with, including, of course, in economy. We have a good example of daily stock price of company here. But then, mostly, unfortunately, astronomy, mostly we have unevenly spaced time series. Think about the radial velocity of the star, cause exoplanet disturbance. This data rich with gaps here. So in this part, it's very crowded, but here it's very scarce. Or think about one effort in astronomical observation. When you coordinate an observation, you have to homogenize the data first before you do any analysis, further analysis. So homogenizing data is another challenge because of different instruments. You have to calibrate this. You have to find, you have to normalize or scale it into a certain level that should, of course, incorporate many technical things that you have to do before you create one light curve of this light event, light curve of the micro lensing event. This comes from combination of data from observatories network, from each observatory, from 3, and then you have to put this into one. That is done before you do any time series analysis. So the idea is, of course, you have to be very keen in looking at the data. The best is, of course, to plot just this as a function of time and observe this, whether to find any trend or seasonality, cycle, outlier, left shift, variation in variance, stationary, of course, this is the easiest one, stationary here, and irregular variation. The left panel shows you data without error. This is the ideal case. But in real, you may find noise pertaining in the data. Then you can see here, sometimes the noise may distract your attention and try to find the pattern of the data. And some may show you this level shift that is also quite common in astronomy. The level shift. Think about the phase shift that I introduced you in the light curve of LP5. That is a sort of a level shift. So in that case, of course, the basic way to do is to shift. But is the shift correct process? Are there any underlying physics so that you can easily shift the level? You need a good reason for doing that. There should be a good reason, physical reason, that give you a good justification so that you can easily shift and try to find variability or intrinsic variability in there. So this must be done before you do any time series analysis, to watch the data carefully, find to for any. Of course, in some aspect, you have to transform this data, transform this into histogram and make an adjustment and then try to get it back, or get the residuals, for example. You try to apply a very good analytic representation, get the O minus C, the difference between all the data to the mean value, and get the residual plot in order to find another variability or the true variability that may happen to the intrinsic nature of the object that you like to observe. Think about, I have a pulsating star, and this pulsating star moving around the second star. So how many periods do you have there? One comes from the pulsation, the second comes from this orbital period. How do you disentangle these two periods? Sometimes you have to take the residual. Yes. First, you have to identify the most fundamental frequency because of this orbital, and then you get one analytical representative, you subtract all the data, and then you can, of course, see the residual and get this and attribute this maybe to the pulsation or spot or something like that. That's not merely due to time series. Sometimes you do this with astrophysics mostly. Time series is a good tool, provided that you use this in a correct way. Okay, so after having this, then what is actually the time series analysis? A beautiful receipt is written by Fagelson and Babu about the methods in time series analysis. But it is applying mathematical and statistical tests to data to quantify and understand the nature of time-varying phenomena. And the purpose of time series analysis for astronomers like us to help us to gain physical understanding of the system and be able to predict future behavior. So if you are correct in making time series analysis, the next generation astronomer will prove that you are correct or not, or falsify you. That is depend on how precise we predict the future based on our time series analysis and our correct time series analysis. And of course, it has relevance to fields far beyond just astronomy. Economists, they use this as well. Yes, time series analysis is one, very essential tools that used by the economists to make a forecasting. While in science, we do prediction, but for meteorologists and economists, they prefer forecasting for this. So the first approach of having looked into the data, the simplest one is, of course, making the preliminaries, the elementary statistics. The best way to do, or the easiest way to do, is get the mean, the arithmetic mean or average of the data set. But again, you have to be cautious about the trend that may, of course, exist in your data, and variance and standard deviation. How much do the data vary about the mean? Fundamental of statistics teach us about the normal distribution, in which we come to the conclusion about the 1 sigma and 3 sigma notion. In 1 sigma, we have 68% data points within this, but if we extend to 3 sigma, we have 99.7% data points. This relates to the level of confidence on how well we distribute, we study the distribution of the data. And then we can extend this to the parametric statistic like mean, variance, median, etc. that can be used for us. And actually, this basic principle is heavily used for what so-called the moving average technique. But instead of using all, we create a bin. The more number of bin, of course, you have the better representation of this. And for each bin, you calculate, of course, the mean and variance, and get the mean as the representative point for one bin. And then you make another bin, and then you may smooth actually this scatter and get the feeling about having look at the trend, or try to gain the trend, to understand the trend or everything that happened in the data. Okay? So this is one thing. And when we make an error analysis of variable data, remember that measurement of mean and variance are not so simple. So mean varies. Is it linear or trend, or they are fading? And remember, variance is a combination of intrinsic scatter, systematic error, and of course, variability, real variability. These are two examples on how this, of course, cause we think that taking a mean and variance is not a straightforward process. In all this trend of the data, there is a variation here. This is the data from atmospheric carbon dioxide measured in Mauna Loa, Hawaii, in our atmosphere. So there is, of course, a cycle within each this, but this cycle is constantly having a positive trend up here. Or time series analysis of this. There are many scatter here that could be systematic, could also be random, but also there are intrinsic variation from here. So the best way, of course, is to transform this into histogram and get and gain your insight about the data, about the histogram. Or you may get this, subtract all the data, subtract all of the data here into this red line and see the residual in order to unfold, or not to unfold, to reveal, okay, this cyclic nature in all of each data here. This is very easy to see because the plotter shows you the line that connecting each point here. But think about no line here. You may see only scattered around here. So one thing that you should also keep in mind, the success of time series analysis is to make a very good visualization of the data. You need to be very good and very creative in creating a graph to gain your insight into the data, because the number is so much. So random errors, to conclude about the statistic and many derivation of time series analysis based on merely statistic is, remember that random errors always present in your data, regardless of high quality the data you have. And please be aware of non-random systematic trends, fading, chart error, observer difference. So the bottom line is understand your data before you analyze this. Okay. So these are all actually the preparation stage. And actually this is what I went through 30 years ago before I come into the time series tool itself. So I remember that my supervisor told me, don't be too excited to use these fancy tools, because making a Fourier transform, making a program is very fascinating for young men like you. But remember, before you plunge all the data into this, you have to carefully look at the data first. Try to transform, try to normalize, try to understand the data before you, because once you move this into the time series, actually you go into another work, because basically I did a frequency domain analysis. Once you transform time domain to frequency domain, everything is quite dark. Unless you have a very effective means to bring it back to your eyes, and then you can see the trend of the data. It's not easy to see the properties in frequency domain, but it's easy to see in time domain, because we are living in time domain. I hope you agree with what I think. So let's come to the method of time series analysis. So there are actually maybe more than 4, but I try to limit my talk into, say, 4 methods of time series analysis. There are many variants of this. the time domain analysis, the Fourier transform, the wavelet analysis, which used to be very popular in the 1990s, and up to now still used. But then it is interesting to see that many people now going back to Fourier transform or frequency domain analysis. The time domain used to be very popular in the late 1970. Maybe the very well-known phase dispersion minimization is very popular on that time. But even though I didn't use this PDM for that. And autocorrelation analysis, the one that has been promoted by Eric in his first lecture, because many astronomers now prefer the autocorrelation analysis and other methods. There are many reasons for this, but use the right tool for the right job. Don't use all the tools for one particular job, because there is no general proposed time series analysis, in my opinion. Imagine that you come into, well, in Indonesia, we have what's so-called Padang restaurant, a very nice restaurant come from western part of Sumatra. Basically, if you come to a Padang restaurant, you may see a lot of dishes. But remember, you have only one mouth. and remember, you have to fulfill the purpose of your stomach. So you cannot eat all. You eat only those that are very suitable for your taste and fill your stomach and create energy for you. So this is a good analogy for time series analysis. So many recipes. But let me share to you my recipe here. First is to gain insight. Okay, I'd like to share how I gain insight into time series analysis. My example, because I'm a stellar physicist, I always like radial velocity. So look at the following radiality. Can you guess what is the period there? Of course, no, because it shows you a group of data here, large object, and scarce data over here. And no pattern can be seen by us immediately. Okay. So what we do, fold the data using the trial period. I think the word folding the data is quite common. For example, if you assume there is a periodicity, there's a cycle, then you may identify or you may guess the period. Guessing the period is very essential here. There should be a period. But when you try to remember that if you have a cycle, then basically there is position where it is ahead of you and we call it zero phase. And then it comes behind this first star, it becomes the 0.5 phase. And then it comes back here, 1 phase or 0 phase again. This is a cycle. So basically what you can do, this whole cycle could be pi radian, 2 pi radian, 360 degrees or 0 or phase 1 to 0. There should be a simple formula for doing this. Normally we have the formula so-called the time that we observe minus the ephemerate or the zero time, and then divided by the period and get the fraction part of that. We call it the phase. Okay, so that's actually the basic recipe in folding the data using trial period. We use the modulo operation. So later on, after we have with several periods here, then later on we fit the result of the folded period. So this is actually the bed that we provide, upon which we fit this with a common analytical function. Normally people sinusoidal function, but also there are many claims on this because sinusoidal is very good for cycle, for sinusoidal phenomena itself. But how about non-sinusoidal, for example, eccentric orbit, or for example, inhomogeneity because disruption in the orbit. So non-sinusoidal phenomena is also very common in astronomy, in which you cannot rely so much upon the sinusoidal function. But as the first approach, of course, sinusoidal function is the easiest one. And as you see here, yeah, many period will introduce you to many shape of this data. And it turns out that you transform this data, on which the x-axis is the time, into the x-axis in phase in this case. Okay, you may see this. Of course, judging from this, you may think that the middle is the best one. Why? Because it gives you a very nice shape of variation and very common in our sense to see variation like this. But is this wrong? Is this wrong? Who knows? And maybe there are two periods, there are multiple periods here, maybe constant shift. So everything can be correct, but then you need a good judgment in time series analysis. So how well the folded data fit into sinusoidal function? When you carry out the frequency analysis, actually you transform this into the power spectra. And remember a very, very fundamental principle in wave. When you match the phase, you have a resonance, and then it gives you a sudden peak or a peak in the power spectra. So the power spectra actually find the resonance between the fitted and the data, and then give you, of course, a sign that there is a period here. But if it comes with more period, then maybe another period come here. This also gives you another shape. So actually, time series is trying to enrich your analysis by combining this power spectra appearance with the phase diagram that you're going to analyze. That's what time series basically do. It helps us to detect any period. And based on this period, actually, you're going to predict whether this may happen in the future, because you basically have this time axis here in which you can apply all of this. Okay, so now these are, well, I may say what actually we are doing with the time series analysis when we deal with the data. So up to here, are there any questions before we go to a specific technique for this?
Do you have any question from participants? Not yet, it seems.
Okay, so let me continue. So yes, after having this in mind, so think about actually time series is easy to do without a very sophisticated tool, and something that you can develop from scratch, depending on the data. Then we come to many tools that have been published up to now. For example, we have the time domain analysis. The time domain analysis, the most primitive time domain analysis is called the O-C analysis. Think about the light curve of an eclipsing binary. And then you try to concentrate on finding where is the time of minimum in this curve. And then you get this. So actually you have already beforehand the ephemeris that calculated by previous astronomer. And then you try to, of course, relate the previous one, the prediction one, with the one that you observe. And then you try to compare the time of minimum that you calculate from your observation and compare with the published one before, the ephemeris one. So what can you learn from that? Whether there is a change in the period, there is a change of the nature. So you actually did a time series analysis on that time. Because in the course of making the O-C analysis, you try to, of course, fit this minimum in the time domain, okay? And then try to get the minimum, the best minimum time for this eclipsing. Okay? And then you got the information of time with a certain precision, usually 3 or 4 digits behind the decimal point. And from the publication, from the previous observation, you got another information about the time of minimum. You compare this with a certain formula, and then you see whether there is a difference. If you believe that the period is constant, the previous ephemeris, of course, can predict the time of minimum that happened during your observation. And then you make observation and you got this. And then you compare with one predicted. Oh, there is a difference or the same. Then you can construct what's so-called the O observed minus calculated diagram using this relation. And this gives you a very important information how constant the period is. So then after collecting from previous observation, Of course, it can be done by other astronomers. And collecting the previous observation is also another endurance, another effort, because you have to look at the previous observation. This is when the data archival publication is very important for you to learn. And then you gather all the data from previous observation, and then you can actually construct what's so-called the O minus C against the ephemeris time. What is time spent between the zero that has been published first with your observation somewhere here? After the time span of several thousand days, because it can be, the time span can be many years, 10 or 100 of years even in one eclipse environment. This O minus C is a sort of a time series analysis exclusively used by binary worker. And now it's, of course, going to be used by exoplanet for the transit study to see whether there is a change in this. But the result is also limited because we lock this O minus C analysis only to study the binary nature, but actually it has a fundamental way of making time series analysis. Why? Because from a very persistent collection of all these ephemeris, O minus C, you may see a very different shape, many shape of stationary of O minus C diagram. It can be stationary, no change in the period, which means that the prediction is get along with this all the observation, or maybe you can make a correction on the epoch and period that has been determined before, because you may see some difference. For example, this is basically stationary but incorrect epoch here. Or maybe in case of P here, you may see here there's an incorrect period here, but it can also be attributed to some physical things that related to the increase of the period from time to time, or decrease of period from time to time, or maybe even both. In this case, in case of D, for example, here, because the zero is not the same, and the shape is also not constant, but it's inclined here. Yes, this is true and simple for linear O minus C shape. But what about nonlinear O minus C? This is something related to the evolution of the star itself. And up to now, it's still a powerful method to gain insight on the nature of binary system in terms of its revolution or presence of free body. So I remember when I published the paper in 1991, when I presented this in the Pacific Rim Conference on stellar astrophysics, some of the binary specialists, they told me, why don't you do O minus C analysis? So my question is simple. No previous observation have been done. So I don't have any data of ephemeris before. So I have to go through a time series analysis. So O minus C is very good, provided that you have a lot of observation before. And think about astronomers nowadays. Do they mind making a constant observation encompassing generation? I don't think that's a trend now. But for example, me, I was grew up at the Bosco Observatory. We did double star work, for example, since 1923 up to now. So we have a long time span of data analysis. But think about modern observatory. Modern observatory may not have a dedicated program to observe one particular object. Why? Because so many objects can be observed now. So when we talk about observational astronomy, that falls into two categories. First, a survey type observation, in which you like to grab as much as possible population of object that you observe and make a statistical study, or aim at one particular object and monitor it from time to time. So the second one is not really in fashion right now. It's not in the really mainstream now. But I grew up on that time when the mainstream was to monitor one particular object and make a deep, in-depth study of that particular object. So that's why O minus C has some limitation, even though it is historically a very beginning of time series analysis in a systematic way and still used until now by binary astronomers, binary stars astronomers, and still used, for example, in it's still published in International Bulletin of Variable Star from time to time. So a good method was proposed by Stellingwerff in 1978 and published in Astrophysical Journal in which he proposed a phase dispersion minimization. Okay. Well, Stellingwerff, as a gentleman, he said that I like to find something that not in the frequency domain analysis, because basically Fourier transform in this era was so difficult to be implemented. You need a computer for doing that. You need a very rigid sample 2 to the power of n to make a fast Fourier transform run very well. So that's very frustrating for astronomer, because basically astronomer has no even space data. Most of astronomical observation are uneven. So the conventional FFT is really not welcome so much by astronomer on that time. And he, Stellingwerff, he thinks that we need to find another way, not in the frequency domain. So he proposed this time domain method called the phase dispersion minimization. The principle is the same. Try to fold data into phases for several trial periods. Okay, so actually you change this. And this formula that I show you here is a formula that transforms your data, which is magnitude or can be any observables with T, the attribute, because it's depend on time. And this T you transform into phase. And how T is transformed into phase is using this one. Take the modulo operation Ti or observation minus T0 for a constant initial epoch, divide by T, get the fractional part. You can even multiply with 2 pi or 100, 600, 360 degree to get in. It's depend. It's quite you have arbitrary for this arbitrary scale for this. But normally we use phase 0 to 1. And what we do after we transform all this observed data into the phase space resulted from this, we make a statistical analysis on this. And that is what the phase dispersion minimization comes from. We compute the mean value of yi, the observable, and then group the folded data into phase bins. Say from phase 0 to 1, you can make 0.1 bin. It's depend on the data. Once again, it's depend on how the data is distributed in the phase space. And then for each bin, you compute variance of data against the mean value of the whole. And sum all the variance, call it the statistical dispersion. And then the period can be obtained if one finds a peak in a plot of statistical dispersion against the trial period. So when you try to construct this, sometimes you have to move back here and fold into the second trial period. And then you come back here, and then finally you get the curve between dispersion and the trial period, and its best dispersion itself. So the best period is related to the minimum dispersion. That is why it's so-called the phase dispersion minimization. When it was published in 1978, all astronomers were so excited because it's easy to develop an algorithm of this and implement this. So I thought that this technique is already classical and not used anymore. But I found in a very new publication in 2014 that this was used by astronomer and published in Information Bulletin of Variable Star as a number 6103 to study the behavior of helium, neutral helium 6678 emission line. The emission line shows double peak here. Now, so there is a violet to red variation of this peak. The shorter wavelength we call the violet, and the longer wavelength we call it the red. When we measure the VR variation and plot this, we have this curve. Of course, at glance you may see there is some small variation here, but not really definite. So what we do, of course, is go through the phase dispersion minimization parallelogram and did what I have already shown you, the algorithm, and plot this against the trial period. And then they found this as the minimum value of the dispersion. And then they come to this conclusion about this is the plausible period and apply this to the phase diagram and get the beautiful variation curve of this emission line in gamma Cassiope. So there is no old method that disposed. They still used, and even up to 2014, that old method is still used until now, and turns out to be very easy to use. For example, if you use the image reduction analysis facility, IRAF, then there is a phase dispersion minimization task that can be used by you there. It should be very easy if you develop this algorithm and make a R script, okay, and then make this phase dispersion. In some of the variable star, AVSO, PSNet, there are some tools that enable you to use the phase dispersion minimization. For those, for example, for those who like to make a survey, because you may get data hundreds or thousand, then you need a quick tool to do this time series analysis. So phase dispersion minimization is one of the recommended tools that can be used by you because it's easy, quickly give you to detect the very fundamental period if it exists, and then you can, of course, concentrate in a large number of objects immediately or very quickly. So the second is frequency domain analysis, and I think after I finish frequency domain analysis, we can make a Pak, is it easy to stop it here before I go to the second?
Yeah, I think we should stop here and have some discussion first before we move to the second session.
Yeah. Thank you. Okay, so let me stop share here because I believe all of you already have the slide, right? Because I put it in the drive and Miss Nimas already shared it to you. So I'm open to any kind of question if you like to ask me. So please do not hesitate.
If you have any question, you can raise your hands. If you don't have, then I will ask Pak Hakim first, if I may.
Yes.
Well, sometimes in our data, it also contains a stochastic quasi-periodic oscillation.
Yeah.
So can the PDM tackle that problem?
PDM itself may have some limitation. PDM is good. You need to go through further step after PDM. For example, make a pre-whitening process. Pre-whitening process means that if you assume a sinusoidal can be represented by the period finding in PDM, then you construct a sinusoidal curve along your data, and then you get the residual from that. So this residual can be inputted into the PDM again, okay, and then you may see another minimum of phase. So you have to do it repeatedly, recursively, until finally you get. So what is good from PDM? It's basically independent of any sinusoidal pattern. Okay? So, but then once you detect the fundamental period, it's quite up to you whether you are going to use monosinusoidal or combination of sinusoidal. It's very much left to your judgment on the shape of the light curve that you see here. If it turns out to be sinusoidal, you can easily plot the sinusoidal or make analytic sinusoidal function and plot it. But if it is not, then there is a problem there, that because you have to find another analytical function that can represent best the fundamental period there. So people usually use a combination of sine and cos based on the period that found by PDM to get the O minus C, the residual, and then the residual can be put into the PDM process again to detect the second period. Or even some stochastic can be found, but it's rarely used for stochastic period because stochastic may means a long question and suddenly there is a variation. There is also a kind of stochastic. So it's quite depend on the data span and the windows of observation of your data. But PDM is superior because it's not depends so much on the resolution of observation. It's just depend on the number of observation.
Okay, thank you very much. Okay, now do we have any question from the participants?
So I'd like to ask who among the participants is quite new to this field?
Okay,
Do not
you can raise
hesitate.
your hands.
Who among you for the first time? Arifin, so this is the first time for you to get acquaintance with time series problem? Yeah, Subham also. Yeah, I see. Not so much, so many. Many of you are quite familiar with this topic. It suddenly comes so much. Okay. So we come to more method in time series analysis. And yes, believe me that comparing to my time series now, it's much more fun and easily to understand. Because in the drive, actually, I put the number of reference. So that reference I collect after sitting in the library more than 1 month during my master student. So remember, I was in Tokyo, and it was in winter, and we have a very good heater, except in the library. So you can imagine, in the winter time, I went to the library in National Astronomical Observatory, which is and the heater was terribly bad on that time. If some of the Japanese astronomers are here, I can share my experience with them actually. So I have to use a cold winter gear and sit in the library with some silicone put here to warm my body, and look into the journals at that time to find the reference for that. Quite a nice moment for me. Okay, I'm waiting for any questions. And
Yes, we have Esan,
yes.
Esan Molly. You can open your mic to
Yes.
ask directly.
Hi, am I audible?
Hello. Yes.
Okay,
Yes,
okay.
Molly. Hello.
So I was wondering, you talked about having two periods at the same time in a system, like when a star is pulsating and it's also in a binary system revolving around some other object.
Yeah.
So how does the time series graph look like in that case? Do you need an OC to see whether the OC looks like it's varying periodically as well, or can you see it in the initial epoch observation that you're taking?
Yes, as Molly, that's a very, very, very good question. I was lucky because I had a long database of observing time. So I came to Japan actually in 1987, but my supervisor, he started observation in 1985. Okay, so basically every year we make observation 1985 to 1988. I remember 3 times. And what is interesting there, when we measure the spectrum and get the radial velocity, I found that the systematic value of the radial velocity in one particular year is very different with the other. Okay, so that's why we don't think about performing any time series analysis for that, because when you put the systemic velocity against the time, you see a very big difference over 3 sigma at that time. So that is why we immediately think that there should be a third body, yes, that actually encircled by this closed binary system there. That needs no time series analysis. But in some cases, when the distance between the binary system with the third body is not so big, then you have to rely on O minus C analysis on that time. Again, O minus C analysis needs a long time span. So what is very appealing here, network of observation is very important. During my time, that character is very strong because we don't have any archival on that time as a Muli. So that's why we need to communicate between observatory. And I think that is the happiest time of astronomer on that time because we make friends. Then I remember I called my colleague from India, make an observation in Nandital, and he make observation the same binary, and he do it immediately and supply the data to me. I was in Japan at that time. We used to make a campaign of observation with Space Telescope Science Institute and India and Mexico and Japan and Hawaii for one purpose of asteroseismological study of NGC 1501. Okay, and it turns out that this sort of observation help so much for phase coverage for that, and to get to of course to look in a more detail on how the variation may see, the hidden variation may see here. The case of triple system that I observe and publish, that's relatively easy because I can see it from the systemic velocity of the radial velocity to detect it. But disentangling the orbital period with the chromospheric activity in which the star has a spot, and this modulation give you another period, that is really painstaking on that time. At this time, I think it should be, in your generation, should be very easy for that. But once again, based on my experience as a referee, people are careless. Information, you are not wrong, but information that
So it was a wonderful lecture. So actually, I was wondering, that might be a very naive question. There is one thing that I came across about Lomskargel periodogram that was also used in Kepler data and test data for exoplanets or maybe for blazars to get the time period of uh, the time period of exoplanets and blazars. So is it similar to time series analysis, or is it a very different thing, that Lomskargel periodogram?
yeah. Subham, I'm sorry that somewhat noisy, so I could not hear that.
Yeah. I think he talks about Lomskargel method.
Long-term periodogram of Skargel.
Yes, and I think it will be discussed in the next session for your time on your frequency domain analysis, right?
Yeah. But I think if we talk about the property, I can share some. Subham, I think basically, when you do time frequency domain analysis based on Fourier transform, you basically try to fit the sinusoidal from infinity to one particular data. That is good as long as you have very well-defined windows, observing windows on that time. So remember, if you have a short windows of observation, and then you try to make a periodogram with the long frequency, you may be suffered by what's so-called the windows effect, the repetition of the windows. Because the box, if you make a Fourier transform of the box, it will give you sync. And then you may have this repeating sync. So trying to avoid this very long, but instead use the what's so-called the Nyquist frequency to limit your observation. Because Nyquist frequency actually will teach you how to limit actually the length of the periodogram that you like to. If I'm not wrong, getting your question right. And yeah, that is a question that usually addressed by people who study transiting or gravitational lens, because it's very nearly stochastic, the process. They like to see whether this period is hidden somewhere by trying to extend the frequency of scanning. That is, well, technically it's easy to accomplish, but physically it's very dangerous, because sometimes you may suffer from alias, or limitation of resolution may cause windows effect in your frequency analysis. But we can discuss about this later in the second session, because we're going to talk about this. So please continue following this, Subham.
Yes, sir. Yeah, perfect. Thank you.
Yeah.
Okay, thank you very much. Now it's now 9:30, and I think we can end the first session, and we will continue it 30 minutes later. We can have a break for a moment and relieve our eyes or make some coffee, but make sure to come back before 10, okay? Because the next session will be start at 10.